Hi, and welcome to a special episode of Operating Systems class. Special because I'm having to record it. I thought we would just do a little bit today. I'm planning on finishing up the material in Chapter 6, and then we'll start on Chapter 7 at the start of next week. This is where we left off in class on Tuesday. We talked about monitors, we had played around with monitor pseudocode, and then we learned a couple of APIs for actually writing monitors. We had just finished up talking about monitors, at least the syntax for monitors in Java, and here's an example of what that might look like. You remember any class in Java can be a monitor. If you want one of its methods to work like an operation or a function on a monitor, all you have to do is stick the word synchronized on it, and that makes it so that any thread that calls that method will automatically acquire the lock on the object before it enters the method. And even if you've got multiple methods in the same object, they all share the same lock. So only one thread at a time should be able to run in any method on a particular object, at least in any synchronized method on any single object. That locking is enough to provide mutual exclusion, but for more sophisticated synchronization problems, we also need something that works like a condition variable. And Java has that, it just has kind of one big condition variable for every object. Threads can, if they're inside a synchronized method, kind of like my picture shows, they can call wait whenever they need to wait on something else to happen, and that will block them. Remember, it puts them in something called the wait set for the object. It'll release the lock on the monitor, release the lock on the object, and put them in that wait set until some other thread comes along, gets into the monitor and calls notify, or more typically, notify all. Remember, that wakes up, for notify all, it wakes up all of the threads in the, or really it takes all the threads that are in the wait set, puts them back in the entry set, and then as soon as they acquire the lock on the object again, they can resume running. So this is the syntax we've got to work with in Java. We also talked about how in Java there is a more fine-grained way of doing monitors if you needed to do that in the future, but we won't really use that in this class. The next thing we're going to do is see how to use Java's monitor mechanism in practice. And we'll go back to one of our first non-trivial synchronization problems, the bounded buffer producer-consumer problem. Here, we're going to make an object that works like a synchronized queue. It'll bury all of the details of the bounded buffer inside the object, and then threads can just call methods on the object whenever they want to get an item out of the buffer or put an item in the buffer. The state for our bounded buffer is pretty much the same as every other implementation we've looked at. I got a variable up here that determines the size, so we could easily change that if we wanted. I've got a buffer itself, which I just made an array of objects. And then I've got a first, which is the position of the item at the front of the queue, the item at the front of the buffer, and then a count of how many items are in the buffer. When we looked at our POSIX implementation of this, we needed a little bit more state because we had to use the synchronization objects that controlled entrance to the monitor and that let threads block when they had to. In Java, we kind of get all that for free. Since every object can be a monitor, we'll just use this object. We'll use the lock that's already on the bounded buffer object that we're making. So that's the state of our object. Continuing looking inside the class, we've got a method for putting items in the buffer. I marked it as synchronized. So just like we said, that's how I keep other threads from running keep multiple threads from running in the monitor at the same time. Once one thread gets into this method, others won't be able to enter the object, or at least any method on this same object, until this one either leaves or calls wait. So insert method is supposed to put an item in the buffer. It's kind of the function that might be called by a producer over and over every time it produces an item. First thing I check on is the buffer already full? If the number of items in the buffer is already at the capacity, I'm going to have to block. And here I just call wait. In our other solutions, we've been able to wait on a particular condition. Like we've been able to say, I want to wait until an empty space opens up in the buffer. But if we're using Java's built-in synchronization method, we can't, or mechanism, we can't be that precise. So we'll just block until someone else wakes us up. And then you can see I put this inside a loop that once we get woken up, we go back up to the top of the loop and check again to make sure there really is space in the buffer. We'll see this, or I'll probably mention this again when we look at the notify call that goes with this. But in Java, if we're kind of using one big condition variable to handle everything that any thread might wait for, if someone signals on that condition variable, they may wake up this thread, even though they meant to wake up a different thread, or even though they weren't able to wake up the specific kind of thread they wanted to wake up. They might resort to just waking up all threads. I'll revisit that and maybe it'll make a little bit more sense later on when we see the call to notify. All right, so like I said, this loop up here at the top is going to keep waiting until there's empty space in the buffer. And then when there is, we just put our item in the buffer. I don't have to worry about mutual exclusion here because I already got it when I entered this method. So if I'm running in the monitor, no one else should be messing with this buffer at the same time. And then on the way out, I just put an item in the buffer. Maybe there was a consumer thread waiting to remove an item out of the buffer. If so, I wake them up by calling notify all. Now remember, notify all wakes up every thread, or really it takes every thread that was waiting and it puts them back in the entry set. It gives them another chance to get into the monitor and run. And this is what I was trying to talk about earlier in this sample code. Here I would really like to wake up just a consumer thread, just a thread that's trying to get an item out of the buffer. But if I call notify all, I'm going to wake up every thread that's waiting for any reason, including maybe other producers that are trying to put an item in the buffer. In Java, if I'm using the standard built-in monitor mechanism, then I don't really have a good way of surgically waking up the kind of thread that I want. So here I'm just using notify all to wake up every thread that might be waiting on something. If a thread like this one up here gets woken up and it can't make progress, it'll just go right back to sleep, wasting a little bit of CPU and scheduling time when it does that. So again, real fast, because I took some side trips explaining this. When we want to put an item in the buffer, we wait until there's an empty space, blocking when we have to wait. Once there is an empty space, we put it in the buffer, and then maybe there was a consumer waiting to get that item. If so, we wake them up. If there wasn't, kind of like a signal on a regular condition variable, notify all doesn't do anything if there were no threads waiting in this monitor. Moving ahead a slide, here's the code for the other side. If you're a consumer, you'll call this to get an item out of the buffer. What it does is pretty analogous to what we just saw. Up here at the top, if you're a consumer and there's nothing in the buffer, if the buffer's empty, you're going to have to wait. So here we make the same call to wait. We keep waiting using this while loop until there's an item in the buffer, until num is non-zero. And then when there is, we remove the item from the buffer. We remove the item from the buffer. Now there's one fewer item in the buffer. And then on the way out, maybe there was a consumer maybe there was a producer waiting to put an item in the buffer, and it had to wait because the buffer was full. If so, we just took an item out of the buffer so that now there's an empty space. If there was a producer waiting for that, this last call to notify all wakes them all up, and then hopefully one of them, at least one of them, will be able to put an item in the buffer at that point. And that's all we need for a working bounded buffer producer consumer in Java, at least for the interesting part of that. So this is a plausible implementation of a Java monitor. Remember, bounded buffer producer consumer is one of our 3 classic synchronization problems. We learn these because they show off different things that show up in real-world synchronization problems, and because they're a little trickier than just made-up toy problems. So they exercise our understanding of synchronization a little bit. We have one more that we hadn't talked about, and it's called the readers-writers problem. The idea here is we might have a bunch of threads. They may want to access a variable in memory. They may want to access a field in a database or something like that. But we want to make sure that if multiple ones try to access it at the same time, nothing bad happens. And that usually means it's okay for multiple threads to read from a thing at the same time. If they both want to just look at, or if multiple threads, however many, just want to look at the value of a variable in memory or look at a field of a database, usually that isn't going to cause any harm. But if two of them want to write to that field at the same time, well, one of them might overwrite what the other one just wrote. And even if there's a mix, if one of them wants to write and some others want to read, that can usually lead to some bad situations. So we want to prohibit that also. So in short, it's okay to have as many readers as you want, any number of concurrent readers. But we can't have more than one concurrent writer, and we can't have a mix. We can't have some readers and some writers at the same time. So we want to build a synchronization object. We want to build a monitor that enforces this behavior so that threads can go to the monitor and ask, is it okay to read right now? Is it okay to write to this thing right now? And they'll acquire whatever kind of lock they're trying to acquire, either a read lock or a write lock. The state for our monitor is going to keep up with how many of each type of thread we have. So if a thread wants to write to the object, it'll get a write lock, and we'll keep a count. This variable NW I'll think of as the number of writers that have a lock right now, and NR is the number of readers. And if we had to say what I just tried to say at the top of this slide, we could say it fairly quickly with these variables. There can't be a combination of readers and writers. So either there better be no readers or there better be no writers. We can't have a mix of readers and writers. And that's what this first part of the condition down here says. Either there's no readers or there's no writers. You can't have some of both. And if someone has a write lock on this field, on this variable, then only one thread can have that. So the number of writers should never be bigger than one. So as long as we can make sure this condition is satisfied, then we should have a working solution to the readers-writers problem, or at least it shouldn't give out multiple locks that are incompatible. So we're going to build this as a monitor. It doesn't quite fit on a page, so I've broken it up into a few different pages. Here we're using our monitor pseudocode, so we're pretending that our compiler understands words like monitor, and we're pretending we can have as many condition variables as we want. So just like I said on the previous slide, our monitor will have two pieces of state. So maybe I wasn't clear about this before. The job of this monitor is just to give out locks. Threads will come to it and say, can I read from this field? Other threads will come to it and say, can I write to this field? And this monitor will grant them access based on who it's already granted access to. So part of its state will be just to keep up with what kinds of locks it has given out so far. And R will be, well, how many read locks are currently given out, and NW is how many write locks are currently given out. And like we just said on the previous slide, at least one of these better be 0. I better not give out a combination of them, and I better not give out more than one write lock at a time. What happens if a thread tries to acquire a read lock when there's already a writer accessing the object? Or the other way around, what if a thread tries to acquire a write lock and there's either some readers or a writer that's been granted access? That thread's going to have to wait until it can acquire its lock, and that's what these two condition variables are for. If a reader wants to get a read lock and they can't have it right now, they'll wait on this first condition variable. Same with the writer, if they can't have the lock they want right now, they'll wait on the second condition variable. So this is the state for our monitor. This is how it keeps up with what it's doing right now. It'll have two functions for the readers. This top one is for giving out read locks. Every time a reader wants to access the object, it calls lock reading. And when this returns, the idea is it has acquired the lock. This function will block until the reader can have the lock it wants. And then it gets to read from the field for however long it wants. Once it's done, we're going to depend on that thread to tell us that it's done by calling unlock reading. So threads will call this first one to acquire a read lock, and then they'll call the second one to release that lock. And we'll pretend there could be any number of threads trying to acquire and release locks all the time. So let's look at what's going on in lock reading. So a thread calls this whenever it wants to read from whatever we're trying to control access to. First thing we do is we try to decide, well, can I give out a read lock right now? If there's currently a writer, if there were other readers, that's fine. You can have as many readers as you want. But if there are any writers, this thread's going to have to wait. So that's what I implemented. While the number of writers is non-zero, you're going to have to wait until this thing is readable. And then eventually, if there are no writers, or if there were no writers to begin with, before you leave this function, you increment the number of readers, because you just got a read lock. This is going to count how many readers have been granted locks, so that when the last reader gives up their lock, we can tell. Whenever a reader gives up a lock, it calls this second function, unlock reading. In this function, we first decrement the count, so if one thread released its read lock, that's one less reader. If that lock ever hits 0, well, that's when writers get a chance. If that lock, sorry, I probably said that wrong. If that count ever hits 0, that means all of the readers have given up their locks. And if there was a writer waiting, then that's their chance to access the object. If there was a writer waiting, they're going to block on this writable condition variable, backing up. That's the one we talked about right here. So if there was a writer waiting, we signal to wake up one of those writers. Here you can see we wouldn't want to broadcast here because only one writer at a time can access the object. So here it's nice that signal just wakes up one of them. And also remember, if there were no writers waiting, the signal does so no harm. It just wakes up a writer if there was one. So these are the two functions that readers call to lock and to release locks for reading. We got the same two functions for writing. Whenever a writer wants to access the object, they call lock writing. And then inside this, we do the same kind of thing. We look and decide, is it okay to grant this lock? And if there are any readers who have been given locks, I can't give it out, so I make the writer wait. Even if there are writers, if there's another writer, I can only have at most one writer at a time, so if I've already given out a write lock, I also have to make this writer wait. Once there are no readers and no writers, then I can give out the write lock. So this thread, so I'll get past this while loop when that happens. I'll increment the count for the number of writers. I am using a count for that, although it should never be bigger than 1. It was easy to write the code so that I just increment the count as I give out a write lock. And then when that writer eventually gives up the lock, then I decrement the count. So then we're back at 0 writers. When we hit 0 writers, well, we know there aren't any more writers, and there must not be any more readers, because if there were, I wouldn't have been able to give out the write lock in the first place. So whenever a writer gives up their write lock, we know that nobody has any locks on the object, or on whatever we're controlling access to. So it's okay for readers or writers to access the object. So I wake up both types of threads. Maybe there was a waiting writer waiting after this one. If so, I'll give them a chance to try to acquire the object. Maybe there were some waiting readers. I'll wake up them and let them access the object. And then, kind of like it says, whoever gets there first is going to get access to the object. If there was a waiting writer, signaling on it here might let it get access to the object next. If there was a waiting reader, sorry, right here, signaling on readable might wake up one of those and let them have access to the object. So you can see, so this is how this is supposed to work. It has a couple of things that we could improve, and the slanty text over here, "Does this work?" should make you nervous about whether or not it's a perfect solution. I can think of two problems with this solution. The first one's going to be easy to fix, and I kind of tried to talk over this issue when I was describing it. But the problem is right here. When a writer gives up a lock, we wake up a reader, we call signal here, and that'll wake, if there was a waiting reader, it'll wake them up here, and they'll get a chance to acquire read access. They'll get a chance to return this from this function. But what if there were a dozen waiting readers? This only wakes up one of them. And if you're going to let one reader have access, you might as well let them all have access, because it's okay for them to have concurrent access. So this would be better if we could do a broadcast, just wake up all readers. But we're not assuming that we have a broadcast in our pseudocode, so we'll have to get by without it. Fortunately, we already know a standard trick for getting around this, and it is, well, if all we had was a signal, if we didn't have a broadcast on the signal, we could wake up the first reader, and then we could make them responsible for waking up we can make each of them responsible for waking up potential readers that were behind them. And moving ahead a slide, that's what I did here. Using the same trick we did really on one of our first simple toy monitors. Here's the lock reading. If we left, moving back, if we left this code the same, whenever a writer gives up access, I'll wake up a reader. It's easy to make that reader wake up any potential reader behind them by just putting another call to signal here. So if a writer gives up access, that'll wake up one reader here, they'll increment the count, and then they'll signal on readable again with the idea that if they've been given read access, then anyone else ought to be able to have read access, at least anyone else that's waiting right now. So that fixes one of our two problems, and that was the problem that whenever a reader is given access, we might as well let a bunch of readers have access, and that was easy to fix. The second problem is harder to fix, and it's a potential problem of starvation. Over here, backing up a slide, when you call lock for writing, you can only get that lock if there are no readers and no writers. Moving ahead to this version of our code, if a reader comes along and there are already some readers, that reader is given access right away. They don't even have to wait here, because if there are some readers, there can't be any writers. So if there are some readers who have access, any readers that come along behind them will also be given access. And even if readers are occasionally giving up access by calling unlock reading, as long as there was a steady stream of readers who wanted access, and some of them were always holding a read lock on the object, writers might never get a chance to acquire a lock. So writers could starve in this. That is something we could fix. It makes the monitor a fair amount more complicated, but normally the way you would have to fix that, or the way you might try to fix it, is by keeping up with more state in the monitor. Backing up to our first slide in the monitor, we're really just keeping up with the number of readers and the number of writers that have access right now. But we could easily add more state to keep up with things like, well, how many readers are waiting for access, and how many writers are waiting for access. And we could implement policies so that, you can think of this method right here. If one reader already has access and another reader comes along, they get to go right on through. But we could change that policy. We could make it so that if there was a waiting writer, eventually readers would start queuing up, so that eventually that writer, or at least a writer, got a chance to access the shared data. That would make that a little bit more complicated, but since we can have as much state as we want in the monitor, and we can implement, as much code as we need to make a decision inside this function, we could make it so that it forced readers and writers, say, to take turns if there were some waiting readers and writers. And we've done that kind of thing in the past, usually as part of a homework assignment. It is trickier than the simple monitor that I fit on the slides here, but it's still something that's doable and doesn't take that much code. Backing up, I realize I forgot to mention one detail on this. Thinking about the readers-writers problem in general, we could compare it to something like the critical section problem. Normally, if multiple threads want to access the same data, we can just wrap mutual exclusion code around that and then let only one thread at a time access the data. Comparing that to readers and writers, or the readers-writers problem is kind of a more fine-grained solution. It permits more concurrency than just mutual exclusion. If multiple writers want to access some data, or a mix of readers and writers want to access it, they can't do it all at the same time. But if it's common to have a bunch of readers or a bunch of threads that just want to read, and if writers are less common, this can give out a lot more concurrent access, which could permit your program to run more quickly, more efficiently. That was our last big topic for talking about monitors. We got a few little things to talk about. What could I tell you about monitors? Well, like I said, monitors, you can think of them as kind of a bigger synchronization method or mechanism than semaphores. They're good for building data structures that have built-in synchronization. And I think we demonstrated that with our bounded buffer producer-consumer problem. Instead of just putting in synchronization into existing code, we could build an object that has built-in synchronization so that threads can access the object, and it provides us semantics so that they, in calling the methods on that object, they automatically get the synchronization behavior that they need. Comparing monitors and semaphores, which of these is a better programming model? I think it depends on the problem. Often when I'm trying to solve a problem, it seems that it might be easy. Sometimes it seems like it's easier to solve with semaphores. Some problems seem like they're easier to solve with monitors. So it's nice to have access to both of these. Strictly, you could get by with just one of them. Monitors and semaphores are provably equivalent. And by that we mean any synchronization problem you could solve with semaphores, you could also solve with monitors as long as you had condition variables, and the other way around. Anything that you could do with a monitor, it's easy-ish to show. You could also do that with semaphores. If we had to show this, the way you normally show two mechanisms to be equivalent, or at least an easy way to try to do that, is to show that one of them can simulate the other, or you could build one of them out of the other. Between monitors and semaphores, I think it's a lot easier to show that you can, if all you had were monitors, you could do everything a semaphore could do, because with a monitor you could build something that works just like a semaphore. You can also make that argument in the other direction, but it is a little trickier. Takes a little more explanation to make that argument. So for my slides, I picked the easier direction of the argument. If you really wanted to make this as an argument that they're equivalent, you'd have to go both ways. But here, to give you a little intuition about this, I decided to show, or to try to show, that monitors are just as good as semaphores. They can do anything a semaphore can do, because you can build a semaphore with a monitor. So you can build a monitor that works just like a semaphore. So here's how we could do it. I made a monitor object. I'm using our pretend monitor pseudocode here. I called it a semaphore, because it's going to behave just like a semaphore. Inside my monitor state, I'll keep a count. And that'll be the count of the semaphore. I'll initialize that at 0, and you can see I'm pretending I have an initialization function down here. When you call it, you tell me the initial count, and I just copy that to that field of the monitor. I'll also have a condition variable for blocking threads in acquire. Remember, for semaphores, if you try to acquire on a semaphore and its value isn't positive, then you have to wait. So I made a condition variable. I called it positive because that seems like what we're waiting for. If you call acquire and you can't decrement the semaphore, then you have to wait until it has a positive value. So that's all the state I need. Let's look down at our two functions in the monitor, and they're called the same thing that you'd expect a semaphore to have. Acquire does the job of acquire on a semaphore. When you call it, it looks at the count of the semaphore, and if it's 0 or negative, you wait until it's positive. So you block until someone increments it. Once you wake up, if it's got a value that's positive now, you decrement it, and then you've successfully acquired. Whenever someone releases, they increment the count, and now if it's positive, after I increment it, so that's why I'm doing the pre-increment here. So after I increment it, if it's positive, maybe there was another thread waiting in acquire for it to become positive. So if so, I wake up one of those threads. And here also, I wouldn't want broadcast behavior here. I just incremented it once. If there was a waiting thread, I want to wake up one of those. So I call .signal to wake them up. If no one was waiting in acquire, no harm done here. So this, if you believe this works as a kind of a simulated semaphore, then it demonstrates that monitors can do everything semaphores can do. With a little bit of extra work, like I said, you can show it the other way around. With semaphore code, you can build something that works just like any monitor you might want. So these two mechanisms are proven to be equivalent, backing up. I think it's nice that we have access to both. Since, like I said, some problems seem to respond better to one or the other. So it's nice to be able to move back and forth between the two when you feel like you need to. That gets us to the end of chapter 6. What do I think we've talked about? Well, this is one of the chapters that we spend some of the most time on. We started out by talking about, by kind of observing that race conditions happen if you don't think about synchronization. We started trying to create our own synchronization solutions, and that's where we came up with things like spin locks that modern operating systems use to provide kind of momentary mutual exclusion around critical operating system structures. But in practice, for application programs, we don't want to have to build our own synchronization mechanisms. We want to depend on our computing environment, on our operating system to provide that for us. And in practice, those usually come in the form of semaphores or monitors. So we spent some time talking about both of those mechanisms, and we looked at implementations of both of those. So at this point, you should feel like you can do a monitor in Java or POSIX API, and same with semaphores. You ought to be able to do that in either of those languages. I think here, getting a lot of practice thinking about synchronization makes it easier to actually use that. So we tried to make sure we got a lot of practice on this, writing our own code, looking at sample solutions for toy problems, and in the homeworks, we'll try to make sure that you get a chance to try out a lot of these different things. Like I said, I think that's the end of our slides. Yeah, like I said, I thought I would just catch us up today, so hopefully that's a reasonable amount of lecture material. This will set us up well to start the deadlock chapter at our next meeting on Tuesday. That's all for now. I'll see you on Tuesday.